Hello everyone. In this section, we're going to use a little bit about what we've learned about quadratics, and we're going to actually graph them to see what their graphs look like. To start, in prior sections, we were using factoring to solve some quadratics, so we're going to do a little review questions with those. So either at the bottom of your most recent homework or in the margins of the note packet that corresponds with the lesson for today, I would like you to try the following 3 questions. This would be super helpful if you were gone the day before, as a little quick preview about what we were covering in the prior sections. So pause the video now. You have 3 questions to try. Unpause it after a minute and a half, and everyone has had a chance to try them. So give these 3 a go to start. Okay, welcome back. Let's go over it. So the first one, it says you got to solve these by factoring. So I need 2 numbers that multiply to make 24 and add up to be negative 11. Let's zoom in a little bit on this. I'm going to see that is negative 8 and negative 3, and then once I solve them, I get x equals 8 and x equals 3 are my answers. The second one, you should have realized this could be written as x squared plus 0x if there's no middle term, minus 49 equals 0. We call this a difference of squares because x squared is squared and the 49 is a square number, as you can see. And when I factor it, I get x minus 7 and x plus 7. 7 and negative 7 are the 2 factors. Positive 7 and negative 7 are also going to be your 2 answers. Turns out the last one can't be factored. X squared plus 0x plus 36. There's no way you can multiply to make a positive 36 and add up to be 0. Can't be factored, which means this is an example of a no solution. Just like when we were solving some linear problems earlier in the year and got no solution, there are times when we could be trying to solve a quadratic and get no solution. So there you go. That's what we were working on in the prior section, mostly focusing on ones like this one over here. This is kind of the key one to focus on. The last 2 are some special cases. So if you would please, though, have out your note packet for the section that should say something about graphing quadratics in the form ax squared plus c. We're going to be graphing by just making a table today, and then kind of picking out how the parent function can be used to get a lot of other ones by doing what we call transformations. So the first vocab word of the day, though, is quadratic equation. Quadratic equations are equations that have the biggest power being 2. You might find that a little strange that they call them quadratics, but the reason why is because the most perfect quadrilateral is a square. That's why the Greeks were so fascinated with them, and then the word continued on through our tradition. So a quadratic equation is a nonlinear, means that this is going to not be a straight line function, graph. A nonlinear function that can be written in standard form as y equals ax squared plus bx plus c. That is what we mean by a quadratic equation in the mathematics community. Any polynomial that has the largest power we call the degree, being a 2. The parent function, or the most simplest quadratic that we could graph, would be in the case where b and c were both 0. We only have the quadratic, the power of 2 term, and a is 1. So y equals x squared would be the simplest quadratic that we can graph. We call that then the parent function because all other quadratics essentially are a transformation of this function. We start by just making a table. We will do this all year. Whenever we get a new function and we don't know what it looks like, we're going to graph by making a table. So when I make my table, I picked the x values negative 3 to positive 3 just to get a nice snapshot around the origin, a little bit to the left, a little bit to the right. And I'm just going to plug values in. If I start by putting 3 in there, 3 squared is 9, so I get 3 9. So this is the point, 3, 9. If I were plotting it, it would be right there. If I put 2 in there, 2 squared is 4, because 2 times 2 is 4. So 2 would be right here at 4. If I put 1 in there, 1 squared is 1. So 1 goes with 1. If I put 0 in there, 0 squared is 0. Then I'm going to start with the negatives. Negative 1 squared is negative 1 times negative 1. It is not negative 1. Remember, when you put that into the calculator, you need to put parentheses around your negative. Otherwise, it won't do the order of operations correctly. Negative 1 squared is a positive 1. Negative 2 squared is a positive 4. Negative 3 squared is a positive 9. So when you graph this, you actually realize that it's a mirror image of the other side because quadratics turn out to be symmetric. When I graph it, it'll look like this then. It makes this U shape that we call a parabola. The word parabola we'll learn here in a moment, is the shape we give to any quadratic shape. So this is the parent function, though, y equals x squared. We already talked about what a quadratic function is. Anything that can be written y equals ax squared plus bx plus c. That shape it makes we call a parabola, the U-shaped figure you get when you graph a quadratic. It comes from the root words para, meaning with, and bowl, meaning like a bowl, like curvature. So it's a shape that has with curvature. That's where we get the phrase parabola. And here's a picture of it. Every parabola will have two features to it. It will have what we call the vertex. The vertex is the point of change. It's where a parabola goes from going down to going back up, or if it was opening downward, like this, the vertex would be where it goes from going up to going down. So that point of change, that sharp point, we call the vertex. That's the point of change, where it goes from decreasing to increasing or increasing to decreasing. The axis of symmetry is an imaginary line, it's not actually part of the graph, that goes right through the middle. It's where the line that you would need to fold if this were a piece of paper so that the left side would perfectly match up with the right side. It's where the mirror is located if this was a mirror image. So the line that passes through the vertex and divides the parabola into two symmetric halves. In this picture, it would be the line x equals 2. The axis of symmetry for a parabola will always be x is equal to some number because it's always going to be a vertical line. First thing we're going to do, so now we know what the parent function looks like. We know what y equals x squared looks like. That's why I've sketched it in the graph, and I believe it's also in your note packet. Now what we're going to do is we're going to see what different features of the standard form equation, what do a and c do. We'll look at what b does later. It's a little harder to pick out because you actually have to factor it first. So we'll look at today just focusing on what the roles that A and C play in changing the graph. So we're going to look at A first. So the first case was when A was 1. So now we're going to make A bigger. What if A is 2? So we're going to make a table. Just plug points in. Put 3 in for X. I'll do this one written out. The rest I'm going to do just out loud. If I put 3 in there for X, I get 3 and got to square it first. So I get 9, I get 18. So when I put 3 in there, I get 18. If I put 2 in there, 2 squared is 4, and 4 times 2 is 8. If I put 1 in there, 1 squared is 1, and 1 times 2 is 2. If I put 0 in there, 0 squared is 0, 0 times 2 is 0. Now, you'll realize when you make the other side, it's just a mirror image. So this has to be a 2, this has to be an 8, this has to be an 18. Then I graph them. So this one I'll do in red, just to compare to the parent function. 0, 0 is still a point. 1, 2, 2, 8, and then already 3 is off the graph because it grows steep. And it'll look like that, and the mirror image on the other side. So I can see that when this number is bigger than 1, it's going to make the graph a little steeper because it grows a little bit more quickly. I'm actually going to show you how you can use the calculator to make a table too. So have your calculator out and ready. If you went up to this y equals button, and you got to follow along with me because I'm not there to help you. So you type y equals, now we're going to type the equation in 2, and then this x button squared. There's the equation. Now I can actually get the table by hitting the table button that's in blue in the top right. So I hit second, and it looks like I'm hitting graph, but I'm hitting table, and it will give me the table. I can scroll up and down, and there's the table of points that I had just a second ago. So you can use the calculator to actually help you fill in the table if you need it. Okay, we're going to go back and try, what if the value I'm multiplying is not bigger than 1, but less than 1? Let's do a half. If you were using the calculator, you go back to y equals. Instead of typing in 2 times x squared, you do 0.5 times x squared. Delete the other parts. Just hit delete. Delete, delete. There we go. Now we have the equation. And you could hit second table. You'd have the table. We're going to do it by hand because it's not that bad. If I put 3 in there, 3 squared is 9, and half of 9 is 4.5. If I put 2 in there, 2 squared is 4, and half of 4 is 2. If I put 1 in there, 1 squared is 1, and half of 1 is 0.5. 0 is obviously 0. Then it's just going to be a mirror image. You could try. Negative 1 squared is still a positive 1. Positive 1 times a half is 0.5. And then 2, and then 4.5. Now I make my graph. 0, 0, 1.5, 2, 2, 3, 4.5 right there, and I can already see on the right side, it's going to be a little wider. Negative 1.5, negative 2, 2, negative 3, 4.5. So I can see, what does A do? A is going to affect the steepness of the graph. As A increases, the graph gets narrower. As A decreases, it's going to make the graph wider. So A affects the steepness. It's like the slope, but we can't say the slope. Don't use the word slope for this because these are not lines. We said that a quadratic is a nonlinear function. So this affects what we call the steepness of the graph. If A is bigger than 1, it'll make the graph steeper than the parent function. If A is in between 0 and 1, it's going to make the graph wider than the parent function. I'm going to ask you to try for yourself. This, I'm actually not going to even ask you to make a table. I just want you to describe in words how all of these graphs would compare to the parent function. The parent function is y equals 1 x squared. So just describe in words how all three of these would compare to the parent function. Then I'll show in Desmos what they all look like. So pause the video now, unpause it after a minute, and you've had a chance to describe just using words how all of these would compare to the parent function and even to each other. Okay, welcome back. So I'll show you in Desmos what this is going to look like. Desmos is a great tool for graphing quadratics because you can easily adjust the window. So I'm going to pull the picture right over so you can see it. And here's what it looks like. So here's our parent function right here. Where is it? Y equals x squared. Let's do it in black. Right there, y equals x squared is our parent function in black. And let's do one at a time. Let's say I did the 5 first. If I do the 5, you'll see it's steeper, right, than the parent function. What if I do 0.25? Well, it's wider because that's a quarter. If I do 50, it is much steeper than the parent function. Now I'm going to just do it in general. So as A increases, my graph becomes steeper. As A decreases, but it's in between 0 and 1, it's going to be wider. And then you'll realize once A goes negative, the graph is going to open upside down and then do the same thing. As A gets bigger, it's just going to be steeper. So A being negative will make the graph open upside down. And there you go. That's what A's role is for quadratics. Now we're going to see what C's role is. So we're going to make tables and then make a generalization. So what role does C do if A affects the steepness? Well, let's make a table. Put 3 in to start. 3 squared is 9. 9 plus 3 is 12. 2 in there. 2 squared is 4. 4 plus 3 is 7. Put 1 in there. 1 squared is 1. 1 plus 3 is 4. 0 in there. 0 squared is 0. 0 plus 3 is 3. Now once I have this side, the mirror image is just going to be 4, 7, 12. And I graph these points. 3, 12. That'll be, somewhere up. So 3 right here. 10, 11, 12. So somewhere like right there. 2 was already at 7. So 2's at 7. Right there. 1 is at 4. 0 is at 3. And then mirror image. And when I graph it, it looks like that. You'll notice the biggest difference is just all the points moved up 3. You might think that it looks like the red one is than the blue one because it's inside of it. The only reason it's inside is because it moved up. If I actually pulled this red one down, can I do that? Yeah, I can. Look, you'll see it's the same steepness as the blue one. The only difference is it got moved up 3. And I added the 3. So what did this do to the graph? It moved it up 3. Whereas on the last ones, you would have said 5 is steeper than the parent function, 0.25 is wider, 50 is the steepest. This one, you would say it moves the parent function up 3. So adding 3 moves it up 3. Now we're going to do one. Well, what if it's a minus? You might guess what it's already going to do, but we'll see. Put 3 in there. 3 squared is 9. 9 minus 4 is 5. 2 in there. 2 squared is 4. 4 minus 4 is 0. Put 1 in there. 1 squared is 1. 1 minus 4 is negative 3. 0 in there. 0 squared is 0. 0 minus 4 is negative 4. Then the mirror image will just be copying these in reverse order. Negative 3, 0, 5, and plot your points. 3, 5, 2, 0, 1, -3, -4, 0, and then the reflection. -3 and 5. And then again, when I graph it, it looks like that. What did this do to the graph? It moved it down 4. Again, you might say, oh, it looks like it affected the steepness. It really didn't. It's just that it was moved down. That's all that happened. It moved down. So what does C do? C affects translations, or what these are called, up and down. If C is positive, it'll move the graph up. If C is negative, it will move the graph down. Does not affect the steepness, though. It affects really where the vertex is located. So in general, this is what you can say. A affects the steepness. We call it a vertical stretch. If A is bigger than 1, it makes it steeper. If A is in between 0 and 1, it makes it flatter. If A goes negative, it'll open it upside down. If bigger than -1, steeper. In between -1 and 0, still flatter, just upside down. What does C do? C is what we call a translation. Translation means to move, so it moves it up and down. Going to give you a chance to try. You're going to describe in words. So on the whiteboard, maybe make 3 columns. You're just going to describe in words. You can even just use bullet points. Using bullet points, describe. Each of these has 2 things that you would say is going on. Describe in words how each of these is different or would compare to the parent function y equals x squared. What transformations occurred? So maybe I'll do the first one so you can try the last 2. So if I were to look at this one, the 2, you would say it is steeper. You could say stretched vertically as well if you want. The +9 is going to move it up 9. So you'd say it's steeper and moved up 9. Now you try the last 2 on the whiteboard. And pause the video now for maybe a minute. Unpause it once everyone's had a chance to try. Okay, welcome back. This is what you should have said. 0.1 is in between 0 and 1, so it's going to be flatter. You could say flatter, you could say wider, you could say compress vertically. It means the same thing. +15 means it moved up 15. This negative means it's going to open upside down. It's actually the same steepness, though, because it's still a 1. -7 means the whole graph also moved down 7. If I use Desmos to show you, here's each of them. 2x squared plus 9, it moved the graph up 9. You'll see there's the vertex now at 9. Next one moves it up 15, and then it is much, much wider. The last one, it opens downward and is moved down 7. So there you go. That is it for today. Thank you very much and have a good day.